Hi guys, today I would like to talk about some symmetries that we find in quantum mechanics, and I will basically concentrate my attention on the rotational symmetry under rotations. Okay, what does it? So let's start from something simple. Suppose we want to describe an object that is with has a certain shape, a rock, for example, and we have some points to describe the object f of x in point t in a certain time, and we have a reference frame of reference if you like, whatever it is, that meaning that we have coordinates to describe the object with some vectors. But then we want to have a different angle at which we look at the object. Suppose we have another person here that is looking at the object, and this is a different person from this one. I think we all agree that the rock should be the same for both of them. But the function that you use to describe g of x of t, which is basically f of rotated x in t, is different from f of x and t. This is clear because you have the same way when you have a vector in a plane. Okay, you have a vector and then you describe it on a different plane, so you have two other axes. This is x and this is y, and this is x prime and y prime. These are different axes. The vector is the same, but the coordinates are different, of course, because as you can see, this number here and this number here will be different from this number here and this number here. So the same vector, red, has a different description in two different frame of reference. This is fine. But the physics should be the same. If the object is falling, the physics should say that the object will be falling. And if we take some time to go to the top of the hill to the ground, t star, this time, which follow from f equal ma, should be the same for both of the observer, if they do the correct calculation, of course, because this doesn't depend on the fact that the object has been looked at a different angle. So this is a kind of rotational symmetry that we should enforce, and the equation should reflect the fact that they are the same. Okay, now I won't be doing this for f equal ma. I will try to do it for the Schrödinger equation, which in some sense can be thought as more fundamental, if you like. Not everybody's possibly agree with this, but I tend to think that way, that quantum mechanics is underpinning classical physics, meaning that we can derive one from the other. But the equation that then I want to show that will give the same result is actually Schrödinger equation, where there is an h bar somewhere here. Okay, this is the one that I want to show you. But twin to this equation, there is another one that I have to tell you about, which is this equation here. Suppose we have this value here, we have a matrix A, we multiply our psi by A, and then we multiply with the scalar product of another psi. So this is the scalar product of two vectors, and this can be written in more detail as A of x psi of x in dx, point to point, and this is the probability distribution of your A of x. So if you like, so there isn't x and the x. If you like, this is the average value of the mean average of your observable A. A can be something that you look in your system. Could be, for example, the rotation of your object, the energy of your object, the position of your object, and the angle, whatever. Some observer, something that you can see in your object. And then we want to see what happens to this value here when we derive it over time. When we do the derivative over time, we need to take care that this is composed by two bits, which is this one plus this one, because this is a product. It's a product, so there are 2 points. There are two components. But now we use equation number 1, as we can see, and we can write that derivative over time of the average value is h a psi minus, and this should be there should be a minus here, because no, let's see, because there is yes, there's an I here. Here we go. There's an I here, and this goes to psi a h psi, which means that the derivative over time of your observable can be written as derivative over your operator over time is the commutator of your operator with the Hamiltonian, because it's hi minus I, like this, and then we can get from this one to this one by multiplying left and right by psi, by your function psi. Okay, so this is just another way to write Schrödinger equation when you want to see what is the evolution of an observable, of something that you want to see in your system, something that you want to measure in your system. Okay, and we will write it up here as a second equation that can be, and there is an hi always, I forgot, but the structure is this one. At the moment I don't want to fixate on all the details, I'm sorry. I will link to the Wikipedia page where all the signs hopefully are correct, but I want you to grasp the idea that is behind. So what it means that there is a rotational symmetry, it means that the equation of motion will give the same results, meaning that whatever our psi of Rx of t modulo square will be, should be the same as psi x of t, because the physics is given by this probability amplitude. Okay, now let's then do an example with rotation in fact, and we have psi of Rx in t. How can we write this? We can write it as psi of sinus theta cosine theta minus sinus theta, and this is a matrix that is applied to your vector, for example a 2D vector x and y. This is in 2 dimension, could be done in 3 dimension, it doesn't matter, just to give you an idea. But we want to do a small rotation because we want to see how this applies. So for small rotation we know that cosinus theta is basically 1 minus theta squared divided by 2 over factorial, and sinus theta is theta minus theta cube divided 3 over factorial, and we will discard the cube and the square because they are small, so we will just use 1 and theta for the moment. So our rotation for a small angle epsilon of your vector t, which meaning that the rock is seen with a different small angle, this will be given by this rotation here, which is epsilon 1 epsilon x. Okay, and t. And this is just one bit, and then there is a whole series of this, right? If you remember, this is 4 to the power of 4, and this is plus theta to the 5 to the minus of 5, and there is the whole series of those. And this matrix here will that I extract from here for small angle is 0, 1, 1, 0, and it's a rotation, as a rotation of a fixed degree. But if you multiply for epsilon, it's a rotation of a small angle. So what happens is that when you have this matrix here that we derive quite quickly by expanding the rotation in small terms, let's see what happens when you do the sum of all of these. So we have 1 minus epsilon your matrix A, which is epsilon A, plus square A square minus epsilon cube 3A cube, and so on. But this is exact applied to your psi. But this is exactly e to the I epsilon A of your psi, which makes sense if you want to have this equation here, because basically if you see the modulus square, it means that you have to multiply e to the minus I ips A star conjugate times e to the I epsilon A psi conjugate, and this must be equal to psi conjugate psi. This means that this is unitary. For example, e to the I epsilon A is a unitary matrix, and means that the conjugate complex of A is equal to the complex conjugate to the matrix itself. Complex conjugate, if you think about in complex numbers, e to the I x is simply e to the minus I x, and the complex conjugate of a matrix is a matrix which is transposed with all the complex conjugates inside. But these are just symbols that I want to don't fixate on those symbols. Just some maths to say that those matrices have some properties to make sense of them, but and especially we think in this we look at the unitary, which means that is written as an exponential of this matrix here. But now, if it's written as an exponential of this matrix here, let's see what happens to the equation of motion that we have, and let's see what it means that the description of the rotation is the same, which should imply that the physics is the same, but also, which actually does in this equation, but also we will see that something else happen, which is hopefully not too far away. I should be quick. So suppose now we have the equation e to the I epsilon A psi divided by t. So we change, we are using the rotation of your matrix, of our matrix. Okay, now this, we see that this doesn't depend on t, so we can write it this way. Psi is here, and this is e to the epsilon I. This is fine. Then we multiply by the complex conjugate of this matrix, both sides actually, which means that it's the same. These are unitary, meaning that they give 1, the identity, so so we can remove it, and therefore we have another equation from here which is basically the one that I'm writing up here, which is, in a second, just a sec, which is the derivative over time of your psi function is e to the minus epsilon I h a I psi. Okay, and this is fine, and then we can expand the exponent. We can expand it, and this should be the same as let's see what happens. We can expand the exponent, which means that is 1 minus I h 1 plus I a plus psi, and this is h psi from the first one, and the second one is plus epsilon h a, sorry, I jumped to conclusion, h a, if I can find a pen, it's okay, minus h a psi. Okay, so we know that we therefore need to have that in order to have the same equation as the beginning that we want, we need this to be 0, meaning that the commutation relation, the commutator of h and a is equal to 0. This is a commutator, meaning that h times a minus a times h, which is, if you remember the first video on quantum mechanics, this is related to the Heisenberg uncertainty principle, which means that in quantum mechanics there are observables that do commute and others that do not commute, which is very different, profoundly different than in classical physics. Okay, but then let's see what it means that these two commute. If you look at equation number 2 here, it means that the derivative over time of your operator, so the mean value of your observable, is equal to 0, meaning that is a constant. So this is an important fact that symmetries implies conservation of some observable. In fact, the symmetries of rotation imply the conservation of angular momentum, L, which is the action of under rotation. The symmetry under translation implies the conservation of momentum, which is P, M times V, if you like. And the symmetries around time translation is the conservation of energy, the Hamiltonian, which is basically saying that H commutes with H. Anyway, but okay, so just to recap quickly, we used the fact that we used the Schrödinger equation, and then we used the mean value of the Schrödinger equation over time to derive the Heisenberg equation, which is this one, and then we use the rotation of our system to derive an equation that is giving the same physics, and the same physics, we use the fact that they give the same physics to have the same result, and by the same result we derive one important fact that if we impose the rotation of the rotational symmetries, there is a quantity that we can look in our system that will be conserved during the evolution of time, and in the case of the case of rotation is the angular momentum is conserved. Okay, and actually it goes by both ways. Okay, I hope you like the video. I will do maybe another one on translational symmetries or other symmetries, I don't know, but the idea, I hope that the idea got through, and follow me for other videos in the future. See you next time. Bye.